This is Precalculus chapter 5, lesson 3. We're on page 345. Okay, there's nothing new in this lesson. This is simple application of what you've already learned. All right? So we're going to apply what you've learned. You know these exponential equations, all right? We talked about this last time. If I'm earning interest over a certain period of time, what's the formula? Interest over a certain period of time. The amount over time equals principal times
ERT.
That's over, like it's compounding every year, every month. It's not PERT. PERT is for what? Compounding
It's
continuously. Continuous, right? When you hear the word continuous, that's PERT. But this is like year compounding, monthly compounding. It's 1 plus the rate to the time. That's for annual compounding. What if it were monthly compounding? The rate is always given as an annual rate, always. So for monthly compounding, you'd have to do the amount over a specific period of time equals the principal times 1 plus the rate divided by 12 times the raised to the number of months. Got it? You have to make your rate a monthly rate. If it were daily, I'd divide the rate by 365. My exponent would be in days. Got it? Make sense? When it is continuous compounding, when you hear the word continuous, then it is PERT. The amount over time equals the principal E. Does anybody remember what E is? When do we use E? It's in our calculator, but it's exponential growth, continuous growth, but it's related to the natural log. Does anybody remember the value of E? It's like pi. It's like not like pi, because pi is 3.4 whatever. 3.14. But yeah, I know. I even said it wrong. The math teacher. Yes. So pi is a different number, but it's like pi in that it's an unending decimal, right? So it's like, 2.718, and it goes on. Yeah, it goes on and on like the value of pi. All right, and E is raised to the RT. What's the R represent? Or the rate of growth. Sometimes this R is going to be a K. So it could be raised to the K, but I always use R because PERT works, right? And then we're going to have one formula at the end, but we'll look at that at the end. All right, let's look at example 1, compounding annually. This one's easy. We're just going to run through these. If you invest $6,000, what does the $6,000 represent? In the formula, what does it represent? If I invest $6,000. That's the principal, right? At 8% interest, that's the rate. How do I just write 8 for the rate? What do I write? 0.08. You convert it to a decimal. Got it? So it's 1 plus 0.08. How much do I have in the account after 10 years? So what do I do with the 10? It's the exponent. Okay, we don't have to do that math. We've done that math. All right? So that's an easy one. All right, let's look at example 2. What if I have different compounding periods? All right, we're going to leave these same numbers. All right, we're going to leave 6,000 and 8%. But what if I wanted to compound quarterly?
It'd be 6,000 1 plus 0.8 over 4 to the
number of quarters,
yeah.
right? To however the number of quarters. Okay, it's 3 years. So 3 years, what would this be?
Oh God.
It would be 3 years
12.
times 4 quarters in a year, right? That's sort of easy way to remember it. 3 years times however many quarters are in a year.
So
All right?
12.
It would be 12, yes. What if it were monthly? What would this look like? Over a period of 3 years. We'd still have 6,000, but it would be 1 plus
1 over
0.08 over 12 raised to the 3 years times 12 months in a year. You following that? All right. Now, what if we decided to do it daily? Then it would be 6,000 times 1 plus 0.08 divided by 365 days in the year. And if it were 3 years, it would be 3 times 365. All right, got it? We can do those calculations, right? You can do those calculations in your calculator. All right, we're actually going to do one. Example 3. If $5,000 is invested, all right, so 5,000 represents my principal. Yes. $5,000 represents the principal. Okay, y'all. I'm going to throw this marker away. And it's compounded, 7% compounded daily. So we have 5,000 and it's at 7%. Oh wait, that's 0.07. Compounded daily. We don't know what the time is. How many days? Remember, our time is going to be how many days. When will the investment be worth $6,800? All right, so how are we going to solve this? We did some of this on Tuesday. Where do we start?
Divide by 5,000.
Divide both sides by 5,000. Somebody do what this is inside here, and somebody do 68 divided by 50.
It would be 136.
This is 136.
It would be 1.36.
This is 1.36. Does it end? Does the decimal end there? Okay. Equals what's inside the parentheses?
I have 1.000.
Okay. 1.00019. Okay, let's leave it there. Going out that far is better than just 1.0. All right. So how am I going to solve this?
Divide by, wait,
When I'm solving for the exponent, I go to logarithms.
so a ln of,
That's the log.
no,
Log. What's my base? This is actually in the next lesson, but y'all should know this already. It's this. It's this.
We had a 50.
1.00019. That's my base. That's my base. What's my argument?
1.36.
1.36 equals T. All right, so you're going to go to math.
We we
On
are.
your calculator. It's in that first column, like way down. Math and go way down. Below summation.
It's
1,618.49. This is the number of days. Because we're talking about days. So they probably want the answer in years. So how do we get it in years?
Divide by 360.
Divide that by 365. Simple conversions. How many years?
4.4.
4.4 years. Got it? All right, so this is nothing new, right? Nothing new.
You know why I said
All right? Let's look.
It was 7.
I want you to look
No.
on page 348. This is how we get E. So we're just looking at what's inside the parentheses. Got it? So if I have, and they just use a rate of 100%, which is 1. Wait, 1 is 100%, yeah. All right, so the compounding period is N, right? N is the number in that period. And so it's 1 plus 1 over N raised to the N. Look what happens to the number as we compound more frequently. So by the time we get to daily, what's inside this parentheses, what's right here, by the time we get to daily, it's at 2.71. What value is this approaching? E, that's right. Look when we get to every second, it's 2.7182825. That is so close to the value of E. So E literally means we're compounding every second, right? That's why we can use E. Does that make sense? That's the only reason we use E is when we hear the word continuous. All right, so that's what these next examples are about. Look at example 5. Example 4 was just talking about E. You know where E is in your calculator, right?
Yes.
Shift LN. Or second LN. You know I say shift, but for this one it's second. The other calculator, I think it's shift.
I use both different computers and a calculator.
Yes. Okay, look at example 5. If you invest $4,000, and let's just compare it. Let's make it $40,000. Let's say we're going to invest $40,000, okay? And let's do annual compounding, and let's do continuous, and see what the difference is. What would you prefer? And 5% 3 years. So 5% 3 years. All right, so this is using PERT, and this is using annual compounding over a period of 3 years, right? It's E raised to the rate times time. So someone do continuous, someone do annual, and let's see what the difference is.
I'm gonna do continuous.
Do continuous. Who's going to do annual? This is the difference between, what is continuous?
46,473.
What are my cents?
That's continuous, right?
36.
Wait, is that continuous? Is that this
Yeah,
one?
That's continuous.
Okay. 46,473,
37.
37. Do you have annual? What is it?
46,305. And it doesn't have
No
a
sense.
decimal point.
Okay. So over a period of 3 years, I'm making more here. Right?
So compound continuously.
Continuous is better. So just think about retirement. You're putting money away. And if you're earning continuous, at the end of 30 or 40 years, this is going to grow so much faster than this. This is like the difference of putting it in your money in a CD as compared to,
An iPhone.
no, this is not, okay, technology wise, that's great. Yes, that's great. But this is more like putting it in the stock market.
Wait, CD, like, this?
Certificate of deposit.
Okay.
I thought you were
Um,
buying CD.
Yeah.
Okay,
like
yeah,
a-
y'all don't even know what a CD is, do
I
y'all?
did. I was just messing with you, but you know.
Okay, so I don't know. I would never put, none of my money has ever been in a certificate of deposit, ever. They just don't earn very much. And they don't compound quick enough.
They're similar to bonds.
Wait, is it a CD as in certificate of deposit?
It is a
I
certificate
don't
of
know what that is. I was
deposit.
thinking you were talking about like music.
Oh, no, it's a certificate of deposit, yeah.
You can buy a whole bunch of compact discs and the price, you know.
And actually, real
Those
estate
metallic discs from.
is a great investment.
What is?
Real estate.
Yes. I don't have any real estate. No.
Okay,
Way.
let's go to example 7. Bacteria growth. Y'all know bacteria grows pretty fast, right? Now is when we're talking about this, this KT. All right. So this is it's still PERT, but they use a different formula here. It's principal. The formula is, what page is that on? The formula is on page 351, but that's for exponential decay. We're on growth. Never mind. Forget it. I was thinking we were on exponential growth. All right. At the beginning of an experiment, the culture contains 1,000 bacteria. So really it's like the original amount, right? And then A, they use this value, no, that's for exponential decay. All right. The culture contains 1,000 bacteria. That's originally. 5 hours later, there are 6,000 bacteria. So originally we have 1,000. We go 5 hours, that's our time, and then we have 7,600. So it's growing exponentially. Assuming that the bacteria grows exponentially, how many will there be after 24 hours? All right, so look, it's this formula. The amount over time equals the amount originally times this rate that we're growing to the time.
So this is the bacteria.
This is the bacteria. And really, a lot of times this is K. They don't use R. They use KT.
So what do they use AO? Amount over time?
Amount originally.
Oh.
Amount over time. And actually, your textbook still uses P. But other textbooks,
Our old one did, right?
our old one, I think, used A originally. All right, so now we have this 7,600 equals 1,000. We don't know the rate it's growing, but we know it's to the 5th power. That's the time. And this textbook uses A, but I'm telling you, most textbooks use K
So we,
for the rate at which bacteria is growing.
so we
Okay,
just solve for K.
so let's solve for the rate at which it is growing. So K represents that rate at which it's growing. So how do I solve for K here?
We divide by 1,000.
Right. We begin by dividing by 1,000. This is just the rules of algebra.
76.
Is it 7.6
I'm sorry.
equals K to the fifth?
So then we take the fifth root.
Exactly. We're going to take the fifth root of both sides.
What's the fifth root of 7?
Yeah, what is the fifth root? So then we get K.
Should be a logical answer.
I don't know what it is. Maybe it's in here. I don't know. What is it?
1.5.
It's 1.5?
1.5002.
Yeah, it's 1.5.
002
Yes.
or 003?
002.
Okay.
There's only 4 right? So.
Okay. All right, so that's our K. Now it wants to know, we still have the 1,000 originally. How much bacteria do we have after 24 hours? So this is what it's going to look like, times K to the 24 hours. All right, so the information that they gave us, we're using to solve for the value of K. We did this last year, so that we can plug it into this second set of data and solve after a different number of hours. So the amount after 24 hours, what do we have? 1,000 originally, times K, 1.5002 raised to the 24. Because our time is in hours. All right, somebody give that to me. What is that?
$1,688,000. Oh wait, no, this is not 16888.
16888.
064.
Is there a point?
064 and then point
6.
0.04.
Okay, there we go.
16.
Yes.
Only a few. I won't put that on file.
All right, let's go to example 9. Example 9. Yeah, we're not going to do all of them. We're just going to do some of them. Yes. This one is where it has a different formula. It's decay. All right, so look on page 352. It gives you the formula for decay. We actually did this last year, but we really didn't do a lot of this. All right, so this is when a substance has a half-life.
Oh, this is the sign.
Okay, yeah. So that over some period of time, let's say the half-life is 1,000 years, okay? That means that after 1,000 years, half of the substance is left, okay? After 1,000 years, we have half of the substance. After 2,000 years, we have half of the half, which is a fourth. Makes sense? That's what half-life is.
So it ends up being like a very long.
It takes forever to get rid of this stuff, right?
Churnable.
Churnable, exactly. All right, so you have, yeah, Chernobyl. Chernobyl.
No.
Yes, it's okay.
Chernobyl sounds like it twice, but
Okay. All right, so look,
It's like a
Yeah.
look at the formula, look at the formula.
Cherbies.
It's P, which is the principal, how much you originally have, times 0.5, that represents the half-life, right? But P, that that half-life is raised to the x over h. X means the time, so it's really t, okay? And h represents what is the half-life for that substance. All right? So look at example 9. When a living organism dies, its carbon-14 decays exponentially. So that's what we're looking at. The amount over time equals principal to the x. I'm really going to write t because I want you to know that's just time. Time over h. H being the half-life. An archaeologist determines that the skeleton of a mastodon has lost 64% of its carbon-14. If it's lost 64%, what is left? What percent is left?
36%.
36% of what?
Carbon-14.
The original amount, right? So what do we have left? 36% of what this was is what's left. Got it? 36% of the original amount is what's left. The half-life is what? 5,730 years. How long ago did it die? So we're solving for time.
Can we divide by p on both sides?
Do you understand what we just did?
Yeah, do they want us to graph it?
No. We're just going to answer time. Okay, they solve it with graph. We're going to solve it algebraically.
Can we divide by p on both sides?
Divide by p on both sides. Yes. Yes. So we eliminate the p. Now, what do we do? When we're solving for the exponent, we go to logs. What does this look like as a log?
0.5 base.
0.36.
This is my argument.
And then just
It's just algebra. Yes.
Multiply both sides by 5.
Yes. And then you solve for t. So this is going to be the time. Okay, so let's think about this. Is less than half still existing? Yes, only 36%, right? So is it more or less than 5,730 years?
More.
It better be more, right? So engage your brain.
8,445.
What is it? 8,000?
445.16.
445.
So it's been over 8,445 years. Okay, do you see how that makes sense? It had to be longer than its half-life.